Sir, you are requested to kindly take over the session, sir.
Okay, thank you, Swati ma'am. Good morning, everyone, and welcome back to the hands-on session. Yesterday we had to stop because the power went out. So today we will start again right from where we left off. Okay. So first I will quickly remind you what we were doing and then I will continue. Just a minute. Is it visible?
Yes, sir, it is visible.
Okay. So yesterday we are trying to design one of my published paper. This is triple band terahertz absorption based. Okay, I have already shown you the structure and the basic designing procedure, how we have to design this final structure. So without wasting time, I am directly going to the CST software where we have already designed this complete structure. And now we will assign its boundary condition and then we will start the simulation and design analysis part. This is the CST file which I have already saved it. So till yesterday, we have completed the simulation part, designing part, where the ground plane is there, then the substrate, and then the resonating structure, which is having a three ring, which have this type of structure in which the outer portion is a circular one and the inner one is a hexagonal ring type of structure. Okay, this is the complete all the components. Now go to this simulation part. Okay, and in simulation three things is required. One is frequency, background, and boundaries. So we will check what is the frequency band for this structure. 3 to 40. Okay, so go to this frequency, put the minimum frequency as 3 and the maximum frequency is 14. Okay. As I am simulating this structure as an absorber, then we have to take the boundaries accordingly. So in the boundary condition, the x-axis and y-axis should be a unit cell because we want to make a periodic structure. And z-axis is used for incidenting the terahertz signal. So I will make it as a open add space. Okay. All these options, I have to choose this open add space option in the Z-min direction and the Z-max direction. Okay, the circuit port is already assigned. Just I just save these changes. Now before doing anything, just we have to check the 1D results. Okay, so for that first we have to simulate this structure. Go to the simulation, home, start simulation. And you can also check whether you have applying this terahertz signal in source at the uh, Zmax direction or Zmin direction. So go to this setup solver. Okay, go to the setup solver, then the excitation where you want to put your terahertz source, whether you want to in Zmax direction or Zmin direction or both direction. So better is to use only Zmax because we already know the ground plane is completely filled with metallic patch. So no need to take this Zmin or the all fluctuate. But you can also choose this one also, so that you get both the you get the results from both the directions. Okay, choose this one also. Then directly click start. Now it is simulating our structure, but I have the simulated one. So I just open these file also because it will take 5 to 10 minutes. So without wasting time, I just open this file where I have already simulated this structure. In this file, simulation is in progress. This is the structure. No need to worry about the color because I am just change this color only. Rest all the materials and other things are same. Here it is showing as a yellow color, but here the maroon one. Okay. This design is already simulated. So go to this 1D results in the navigation tree. Go to this 1D results. Here, this S parameter, I have to check the S parameter first. Here, all the S parameter will come. Okay. Where the second one is, this is the input side and this is the output side. Means from where you have to applying your signal, and this is the second port. So this, if I am checking the S11, because we already know for the calculation of absorption, the formula is just a minute. See this one. This is the complete formula for the absorption, in which the absorption is directly we will see say the absorption is 1 minus S11 square minus S21 square. Why we are squaring it? Because the S11 is a magnitude part only. Okay. When we square it, then it will convert as a power term because the absorption is in terms of power only. Then the final formula is 1 minus S11 square minus S21 square. That means for better absorption or unity absorption, we have to reduce these two things. The S21 should be nearly 0 and the S11 also should nearly 0. Okay. And these S11 and S21 components also have its co-components and cross components as well. That means this S11 is having their co-S11 component and cross term, and this S21 is also have its co and cross term. So we have to take all these things, but already we know we are not making this structure as a polarization converter. So it will not, we know it will not convert the structure into co to cross. So by default, we are not taking it into account. But in better manner, we have to take these terms as well. But in case of this absorber, we assume that our S11 cross term and our S21 cross term will be nearly zero. So we omit these things and we directly conclude our equations as 1 minus S11 square minus S21 square. We also know as this structure, the metallic, because of this metallic ground plane, our S21 is also 0. If I am incidenting our signal from the port 1, I am assuming it as a medium 1 and the lower portion of this structure as port 2. That's why I am calling it as S11 and S21. S21 means signal is coming from S11 and is going to port 2. Okay, so we will also assume that our S21 is also nearly 0 because of the complete ground plane. So in most of the cases, you will see the absorption is directly 1 minus S11 ka square. Okay, but we must check these terms also, whether it is completely 0 or not, because it depends on the skin depth concept. What thickness you are choosing in the ground plane. What thickness you are choosing. Is it uh, in accordance with the skin depth concept or not? If the thickness is very small with reference to your signal, incident signal or the frequency, then it may be possible that some signal will transmit at the medium 2 also. That will affect your absorption value. The total absorption will decrease because it has some value. Suppose it have 0.2 value, then your absorption is directly 1 minus, suppose it is 0, then 1 minus 0.2, 0.8 means 80% absorption we will achieve only. So thickness should be as much as like no transmission will take place. Okay, this is the concept of how you are choosing this formula. Now go to the structure. Okay, see the all the S parameter will come. This S Z max. This is our S11. Okay, this is S11. Why this is S11? Because max is medium 1 and min means medium 2. The back side. And the front side is max. Okay. See this S11 results. It is in dB. When we have to see it's in the magnitude part, here in the 1D is in the 1D plot. Go to this 1D plot, this linear term. Now this S11 is a magnitude of S11 and the previous one is in dB. Okay, so we clearly see that at this frequency and this frequency, because in the structure there are three resonating geometry, and the all the three resonating geometry are responsible for one one each uh, resonant frequency. That's why we are achieving a triple band absorption here. Okay, so uh, that we will check at this frequency, this frequency, this frequency. Our S11 means our reflection is very less than 0.1 reflection we got. Okay, that means in the formula less than 0.1 reflection and S21. We will also see the S21. In all these cases, what will be the S21? This one. S Z min Z max. Z max means 1, Z min means 2. So S21 is this. See its value. It is e की power minus 66. When we see both the things simultaneously, then just click to control key and tick both these as parameters. Okay, this one. This is Z max 1, Z max 1, max 1, max 1. This red color. Okay, this is S11 and this is S21, which is nearly equal to 0 because of the ground plane. Okay. If we want to check it, the exact, what is the exact value of this frequency, then in 1D plot, there is a curve marker. I have already shown you. Click this, double click on this curve. Okay. We don't know exactly it is reaching of the minimum point or not. Then just right click here. Okay. Snap to global extreme, snap to extreme. Okay. Now it goes as the minimum point where the frequency is this one. This is the frequency for the first resonant and the corresponding its S11 value. You can also click here also, then click right tick and snap to extreme. Suppose I am clicking here at point 1. Okay. Right tick, snap to extreme. Okay. These are the three resonating frequency in which our structure is resonate. Just write down these frequency values because we have to check the electric field and the magnetic field distribution from for these three frequency only. And we also check the impedance matching concept because if the S11 if the S11 value is very less at that point, that means the surface impedance is matched with the free space impedance, that is 377 ohm. We already know the the free space impedance is 377 ohm, or we can call it 120 pi. So we have to check its surface impedance, normalized surface impedance, where we have normalized its impedance with respect to the free space. This frequency value is 4.6296, 8.3099, 12.6309. Okay. This is the S parameter. We have to take care the these two parameters only, and the if you want to check the co and cross, then you have to see these 1 and 2 values also. Okay. One is the co component and the 2 is showing the cross components. Okay. Save this. Just close this S parameters results. Okay. S parameter will come. And if I am checking this in this file, till now, Here it is showing here at the bottom in the table, it is showing a plus symbol because I am already applying the absorption and impedance equation here. That's why it is showing its results in this section. But in the present file, which I am simulating today, here no plus symbols are present in this time. Why? Because I am not applying any post-processing results here. Only the S11 results will come at the time of the simulation. So just go to this 1 day results and see the all the things. See, in this case, in the S parameter, only this one results will come. But in this case, all the S parameter components will come. Why? Because we are choosing the all fluctuate, all plus fluctuate. We are not choosing only the Zmax term. If I am choosing only Zmax, then the complete, in every cases, the signal is only incidenting in the Zmax medium, means from the front side only. No backward direction impedance signal will come. But when we are choosing all the both the port, then the max term is also present in the input side and the min term is also present because signal is incidenting in the both the directions and the complete S parameter will come. You can check what will happen when we are incidenting the signal at the back side. You can check here. I'm not going into this part. Okay, this is the S11. This is S21. This is in terms of dB. Just I am taking this linear. It is converting it as a magnitude part. Okay. Now go to the post processing. After achieving this as parameter, go to the post processing. In the post processing, here result templates. In the previous lecture, when I am talking about the metamaterial concept, then in the result template, after achieving the S parameter in the result template, I am choosing this S parameter term. Okay. But when we are applying any formula, whether it is for absorber or it is for PCR or it is for any filter or impedance, then we have to choose this as general 1D. Okay. This one. Go to this section. Then in the second term, mix template result. Go to this section, mix template result. Here one pop-up will come. And now in this part, you have to write your equation. If you want to mention the S11 and S21 both, then write it here. If you want to your S11 co, S11 cross, S21 co and S21 cross, then write it here only. And if you want to write only 1 minus S11 square, you can write it here. Okay, whatever formula you want to applying for the absorption, you have to apply it. But first, we have to select these terms what is A, what is B, because in the equation, it is not directly observe the S11 or S21. No, don't mention it like this, 1 minus S11. No, this is not correct. First, you have to choose what is A, what is B. Suppose I am giving in A, just give it as S11. Means whenever I want to use S11, we have to write A only. Okay. In the B, select this max min. Max min means S21. Choose this term. Now, both the term I have mentioned as A and B, just like in your C programming and any programming, you have to mention the values. Now, 1 minus, because this S11 have its real and imaginary part and it is a complex term, then you have to use as only a magnitude part. So ABS means absolute part of S11. I have to choose. Okay. 1 minus ABS A square minus ABS square. Okay. Evaluate, done. If there are multiple parameters, if you are running, you have already done, then choose this evaluate all term. Till now, only one simulation results are there, then I am just choose this evaluate only. Okay, close this. This is the absorption curve. This is the absorption curve, which is, close this as parameter. Go to this, see, this term. Go to this table, then 1D result, then this is mix 1DC, and which is having your absorption curve. Okay, it is similar. Okay, it have 3 absorption resonant frequency, and this is the complete curve, and the absorption is nearly unity. You can see it reaches nearly 1, and you can also choose its exact value by applying this curve marker, and you just mark the press the M key. Okay, with this M key, go to here, extreme. It is already extreme. There are little bit shift in the result. Why it is? Okay, okay. At the final structure, the R1 value is 4.9 and R2 value is also 4.9, which I am using in my paper and in this design, CST design. But yesterday when I am designing this structure, I am choosing it as this R1 is 4.9, that is okay, but the R2 value is not 4.9, it is 4.8. That's why there is a little bit difference in the resonant frequency. No need to worry, whatever dimensions you are choosing, accordingly your absorption result will come. This is not an big issue. Okay, but the small, you can observe the thing, the small variation in any parameter will affect your absorption results as well as your resonant frequency. Okay, this is the part till now we are covering. We are designing the absorber structure we will see how we can observe its S parameter, and we will also observe the uh, how we can put the absorption formula and how we can achieve this absorption curve. Okay. Now after that, after the S parameter and the final absorption formula, we have to check the normalized impedance also. Okay. What is the normalized surface impedance for this structure? We have to see at the resonant frequency what will happen. For that, just go to the paper. See, I have already mentioned all the theory related part in this paper. Absorbers impedance theory. This is the basic absorption equation. When we have normalized it, the normalized formula is Z effective upon eta naught. Eta naught is free space impedance, which is 377 ohm. And after applying all these terms, the final equations for the normalized surface impedance is this one, the equation 3. When we are calculating the normalized surface impedance for any absorber or any structure, then you have to put this formula. And in this formula, we can also solve it because we know due to the metallic ground plane, transmission coefficient S21 is almost 0. So put this value 0. So we can remove this S21 part because in both the term S21 is 0. And the square term will cancel out this square root term. So the effective normalized surface impedance can be calculated as this only, 1 plus S11 upon 1 minus S11. In this S11 and in this equation 4, this S11 and S11, I am not putting it in a mod because that will give you a real value only. But we know the impedance is a complex value which have its part and imaginary part both. So directly put S11 and this S11. Okay. 1 plus S11, 1 minus S11. Just go to the CST. Again, I have to apply it as a formula. So where we have to go? We have to go in post-processing. In post-processing, again in the result template. In result template, this is okay. General 1D. After that, choose this mix template results for writing any equation. This one. There is only one term S11. That's why choose this A only. In the A, rather than mix 1 DC, we have to choose this S11. Z max, Z max. Okay. This A is S11. Now, what is the formula? 1 plus S11 means we have to A divided by, again in bracket, 1 minus A. That's it. No need to use the ABS term here. Clear? This is the formula for normalized surface impedance. Click OK. Now the absorption is, result name is mix 1 DC, and the surface impedance, normalized surface impedance result name is mix 1 DC underscore 1. After evaluating it, it will come here in the 1D result, mix 1 DC. Evaluate. This is the part. Close. Now, this is the result for your normalized surface impedance. But how we can observe that whether it is perfect for our absorber or not? For that, you have to know some basic concept about the normalized surface impedance for any absorber, which is this one. At resonant frequency, impedance matching between absorbers, because we know when we have the unity absorption, that's why you are calling it that frequency is as a resonant frequency. At resonance frequency, your absorption is unity. Your absorption is unity. That means impedance is perfectly matched. And if the impedance is perfectly matched with space, when you are normalizing it, then the real part of the normalized surface impedance is 1, and the imaginary part of this normalized surface impedance is 0. It is not exactly 1 on 0, but nearly you can get these value. Then only you are uh, claiming that your absorber top surface is matched with the free space. Okay, real part is 1 and imaginary part is 0 in the resonant frequency. Because firstly I am mentioning these values, but for this structure, exact resonant frequency value is this. What is that? 4.782, 8.434, and 12.559. This is the final resonance frequency for our structure. Okay, there we have. Just close this result. Go to the impedance result. Now see, in the 1D plot, in this 1D plot, this real and imaginary term, just click its arrow. Real. Right now only real part is shown. See, only real part is tick. That's why only real part shown in that screen. This is the imaginary and this is real and imaginary both. So choose this real and imaginary both. Now this is the real and imaginary part of your normalized surface impedance. It is very difficult to observe it because we have to check in this region only for 0 and 1 only. In some cases it will goes very high, but we need not to bother about it. We have to check only for 0 and 1. So I can change my y-axis scaling for the better representation. I can change this. Where? Here only. These two terms. In the 1D result, in the 1D plot, there is an x-axis, there is y-axis. In x-axis, if you change your, because see, in the x-axis, this is 3, this is 14. That's why here only it is 3 and 14, which I have applied earlier. It is in auto mode. We can change its value any time, any. Right now, I just want to change my y-axis. So put my y-axis as -2 only, because I have to see 0 only. Okay, 2 or -5, plus also +5. Now this one. Now the 0 line will clearly present here, and the 1 line is also present here. Okay. Now what we have to do? We just go to the that frequency. What's your resonant frequency? Here, the first resonant frequency is 4.782. Then go to this axis marker, this one, axis marker. Select this and go to the 4.782. 4.7. Sorry. Some like you can also zoom it for the exact value, but near about we can take. This one. After zooming it, again press the space key so that you can get your initial result. See this one. For this 4.782 terahertz resonant frequency, this dotted line is your imaginary term and the solid line is your real part of this normalized surface impedance. So the real part of this is close to 1. It is 0.85 because if 100% 100% matching is not possible. Okay. But our target is to achieve as much as high impedance matching you can get with the help of your resonant structure. And the imaginary term is also nearly zero. Okay. These two terms are zero. Again, if you want to check this for, we will check second resonating structure. Then okay, we can shift these in. It is clear. For this resonating structure, the real and imaginary part are in accordance with the theory, which says your real part of this normalized surface impedance should be around 1 and the imaginary part is around 0. Okay. Go to the second 8.434. For this somewhat here. Just we can let it, this is the value. So here also this thing is matched. That's why this impedance matching is important. First result you find out your S parameter, then go to the post processing, put the exact formula for your S parameter, but make sure it not uh, contain its magnitude part. It's not contained its absolute part. It should have both the component, real and imaginary, because the impedance is a complex term. Okay. I think this impedance matching term is clear for everyone. Close this. And for this frequency, if you want to check your for the analysis of the physical mechanism of your structure, means in general we know in general from this result we know as the size of the resonating structure decreases because lambda is C by F. So as the size of these, because the outer ring have the largest dimension. This is in medium, this is smallest dimension. And as the dimension of your resonating structure decreases, your frequency will increases. This is clear. That means with the help of this equation, we know that the outermost structure is responsible for the first peak. The middle structure is for this middle peak, and the inner one ring having a lowest dimension have the maximum resonating frequency. That we will know, but how we can uh, analyze these things, and these things will be analyzed by using the discloses. And these things we can analyze by with the help of the field monitor, and we can analyze the electric field distribution and the magnetic field distribution or the surface current distribution. Okay, so I will show you how to check the electric field component at that resonant frequency. We only have to check the electric field distribution and the surface current at the resonating frequency only. No need to check anywhere. For that analysis, again, go to the simulation part because we have to simulate it. Go to this simulation part. Okay. In the simulation, this field monitor. Previously, just check it in the navigation tree. In the navigation tree, there is a term in between field monitor and no fields monitor have been applied till now. We have not applying the any frequency and any type of field here for this geometry. Go to the simulation part, then this field monitor. In the field monitor, the type we have to choose E field if I am analyzing the electric field distribution, and if you want to check the H field and the surface current, then you have to choose this term. Go to the down, this frequency. Here, the frequency term. What's your first frequency? Frequency value is, write the exact frequency, resonant frequency of your structure, 4.6296. Okay, this is the term. Just apply. See in the field monitor. In the field monitor, the first monitor will applied at frequency 4.6296, and this is E field because I want to apply E field. Again, after applying the first frequency, again you can change your frequency value. Just put the second resonant frequency, which is 8.3, no, 8.434. Okay. Apply and the OK button. Both are similar thing. Just choose tick OK or the apply. After applying it, in this section, you can see your setup. Is it is here or not? Then again, for the third, 12.559. Okay. Then again, press. And now if you press apply and then press OK, I will show you. If you apply, then the third resonant frequency will also apply. Okay. All the three frequency and their electric field have been applied. After applying it, if you press OK button, it will show you a monitor with this name already exists. Okay. That means either you have to choose this apply button or you have to choose this OK button. If you choose apply and OK both, then it will just ask you, do you want to replace it? Either you have to replace it or just tick there no and the cancel. Both are similar thing. I just replace this. Field monitor is applied. You can also select surface current. Go to this term. Again, put all these values. 4.782, apply 8.434. Again, apply. The third resonant frequency is 12.559. Okay, directly okay. No need to click apply button. See, all the things are here. E field, H field. Okay, surface current is also present in the H field component. Okay, you can directly start your simulation, or for our convenience, I have already simulated this part. Okay, this is my simulated file. So see here in the field monitor, whatever I am applying in the present file, which is already there based on its own resonant frequency. Field monitor. See, in the field monitor, all these three resonant frequency, I have applied its H field and E field component, and where its results will store, it will store in the 2D, 3D result. Just close this 1D result, close this. Yeah, close this 1D result. Just take this 2D, 3D result. Okay. In 2D, 3D result, that will also run. We can check here only. Here in the 2D, 3D result, take the plus symbol. Here E field folder is there, H field folder is there, the surface current folder is there. Suppose I just want to check my electric field distribution at the top surface of this resonating structure, then I need to go in the E field plus symbol. Then because my structure, because in this structure is run at both the port, that's why here all the for all the frequency, both the terms are there. Okay, both the terms and both the polarizations are there. But in my final file, see, only for the electric field, only 6 part will come. Why only 6 part? Because there are 3 frequency. Okay, for each frequency there are only one port, which is Z max, and for that one port and that 3 frequency, 2 components are there. One is its co-component term, and second one is cross. We have to check only co-component term, means where the one will written here, that we will check. And here 12 result will come. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because for all these frequency and co and cross term, there are Z max and Z min also. Okay. Then first I will check. This is my initial file. This Tuesday one is. So just go to this 4.6296. Just click this file. Okay. You can't observe anything after clicking this E field directly. See, nothing will clear for you. So go to, just take the right tick in any term, select component, In this, shows what you want. In the x-axis, you want y, z, normal, tangent. So we have to choose this absolute in the surface of the structure. What will happen in the surface of the structure? Right now, in your screen, whatever E field is showing is only in the z-axis, not on the top surface of this absorber. So just choose this absolute ABS term. See, press 5 for the front view. Just zoom it, zoom it. Abhishek wants, please unmute me. Yes, Abhishek, please ask your doubt.
Sir, I'm using CST 2024. Uh,
2024. Okay.
yeah. In this, my when I simulated this same the E field and H field and the surface current, when you
Hmm.
click on the right click, na, sir, my menu
Hmm.
is different and your menu is different. I don't get that
What
select component.
this select
I'm
component is not
not there.
in your
I'm getting
structure.
select field, delete, plot properties, and color ramp only.
Then in this section, this home modeling simulation post processing 2D 3D result,
Okay.
there must be that term from where you have to choose your absolute value. You just have to check in your version where this term is there, but it must be there.
Okay. Some a plot
Just
property
check.
is there. Plot properties, like you are also having plot properties. In this, is it
Property is
available?
the different thing. Plot property is a different thing where
Okay.
can where you can change your density and the color ramp signal, and the arrow position, that we can change it here.
Okay, then 2D, 3D
Just check,
plot.
just check in your system, because I'm not using the 2024 version, but we have that version. If you are not getting that absolute term from where you have to choose this select component, I will reply you.
Okay, sir. Okay, okay.
Okay,
And
because we
and
have
one.
2024, but right now I am using this 2021 version.
Okay, sir. It's okay, sir. One
Hmm.
more doubt, sir.
Yes.
What to infer from these diagrams? E field at frequency of 4.629.
What to
What to
differ
infer?
means?
Infer हम इससे क्या इंफॉर्मेशन निकालें?
Infer that
हाँ.
uh, initially I am telling that thing, the electric field and the surface current distribution is for the analysis of your uh, physical mechanism of that structure. Because
Okay.
this is a simple structure with which I am designing. Okay, there are only
Okay.
three components, and all the components are resonating individually.
Okay.
No one are because the coupling is not there. Okay, it may be, see, after seeing the result and after looking into your design, okay,
Mm-hmm.
if there are three resonating structure in your design, then it it is 100% sure that you will get the three resonating peak. Okay,
Okay, sir.
that
Yes,
is
sir.
the basic one. But it may be possible by using these three structure or by using the four structure, you will get more than three or more than results, right? How fourth structure will come?
Sir, your voice
That
is
fourth,
not.
the help of some between two bits. You are getting my point or not?
Yes, sir, I understand that. So we have to design the
Yeah.
physical structure like that if we are getting electric field on that surface or not.
How much resonating frequency you want, depending upon you are designing
Sir, your voice is lost. Even I can't hear anything.
your resonating structure. And resonating structure is something hello.
Vikram sir, sorry to interrupt you. There is some, I think, network issues from your side. So can you please repeat? The participant is asking, there is some voice issue, sir. From the internet side, I think, yes, there is some issue.
Not working properly today's morning.
No issue, sir, no issue. Sir, you can continue.
Right now, not. No. For 1 minute, I will. Hello.
Yes, sir.
Yes, sir.
Hello, Swati.
Yes, sir, you are audible, sir.
Ma'am, right now it is okay.
Yes, sir. Yes,
Yes.
sir.
You can continue, sir. It's okay, sir. You are audible.
Hello, I'm now
Yes,
it is
sir.
Yes, sir.
Yes,
Yes,
sir. Yes,
sir.
sir.
Okay. So what I'm trying to say is, if you have three resonating structure, you must have three resonant frequency. Okay, and each resonant frequency is responsible for one each resonant frequency. But suppose if your structure is having three resonating structure and you got the four resonant peak, then it may be possible that there may be a coupling between some of two terms coupled, and that's why the fourth peak will come. And which two structure will coupled, that we will observe with the help of this electric field and surface current distribution. Means in general we can say the behavior of this physical mechanism of this structure we can observe using the electric field and surface current. Okay.
Okay, sir. Okay.
Yes. Hmm. Now what we have observed, yeah, this thing. I will reply you how you can see your this component, select component and this absolute term. Okay. Right now, as we take this absolute term, this electric field will come. Okay. Then here, go to this magnitude dB part. I just want to uh, this term we will see in terms of dB only. So I just change my unit as dB and maximum with respect to 0 dB. Okay, the maximum electric field is shown as 0 dB, and after that all the dB value will decrease. Means I just want to normalize our electric field value. That's why I am taking this max 0 dB, so that the representation of this electric field will more easier for me, because right now I have to adjust my scaling. This is the scaling for electric field with respect to this resonant frequency. Okay, this is different for each and every cases. Depending upon the electric field value, this scaling of electric field will change. So how can we change it? In the 2D 3D plot, this minimum and maximum value and this unit volt per meter, these things is responsible per, but it is very difficult in volt per meter. I can change this thing. So better is change it in dB and put my maximum value as 0 dB. Here in the scaling, the red one is showing as the maximum electric field, means where the electric field concentration is more, that will represent as the red color, and in a similar way it is decreasing. Now see the structure. Here the complete part is blue and the little portion is green at the top or the bottom side, because the vertical axis, this one, in general we can say it as a y-axis. The vertical direction is the electric, yeah, the direction of this field is this. The field is resonating from here to here, the electric field, and it is very common if the electric field is like this, then if we check the H field or the surface current, it will in this direction, because both the E field and H field are orthogonal to each other. E field is like this, H field is like this. So, but we have to change the scaling of this electric field component so that we can clearly observe all the colors, because right now I am not seeing anywhere red color. So how can we analyze where the electric field concentration is more? So choose this dV part as 0 dV. Now this will change it as max 0 dV to min minus 10, and you can also change here also. Okay, if you put minus 50 and here minus 5, it depends on your representation and your scaling value. See this one, minus 40 is far better. And if you want to red this color more, then minimize your maximum value, minus 15 is this. Now this is the scaling for electric field at this frequency, and this is the electric field distribution which observed at the first resonating frequency. Sorry, take this pen. See, this is the first structure, this one the second, and this one the third. And the third resonating structure have more electric field distributions. Means electric field concentration is maximum at the third peak, third ring. And we also know, as I already told you, the resonating frequency value is, the dimension of this is high. That means it is responsible for the first peak. Okay, it is responsible for the first peak. Similarly, you can also observe the second. This is the second frequency now, 8.434. Yeah. See, it rather than the outermost ring, it will come, the electric field will confine at the second ring. And you can also change the scaling, then only you got the proper visualization. Minus 45 with minus 15. See, this second resonating structure and the gap between these two are responsible for the second peak. Similarly, you can observe your third peak. It is very high, so reduce its value. Minus 12, 40. See, now this is confined at the center of this structure for the third peak. This is the way we can observe the things. At the end of this hands-on session, I will give you an assignment for all of you. I will give you a one paper and you have to submit it. Okay. And that will be counted for your assignment mark, in which you have to do only 3 parts. Just simulate this, just design that structure. That is the first part. Then simulate it and find its S parameters and the absorption value. This is the second part. And the third part is to find its electric field distribution at the particular resonant frequency. These are the 3 work which you have to done in your assignment task, which I will give you later. At the end of this hands-on session, I will give you the paper name. You can download it and you can make it by own. Okay, this is the electric field distribution. The direction is from top to bottom. Now, if you observe the electric field for the H field, sorry. See this H field clearly. See, I will change its unit so that you can observe it properly. Okay. This is now. Yes, Abhishek, we will cover these things. Let me go to the one by one way, because I know you know some part of this simulation thing, but most of the participants have not uh, able to do these things also. So that's why I have some curriculum and I have to follow the procedure as well, what topics we have to cover. And later on, as we go in this hands-on session, we will cover all these topics. Don't worry. I will cover it by today itself. Okay. This is the electric field. This is the magnetic field. And you can observe the surface current also. The better way is the electric field and the H field component you are representing with the help of the contour plot. In the 2D 3D result, just see this section. This is the fourth section is contour. Okay. And here this is the term, Abhishek, if you see in your 2024 structure. I think maybe here it is. Yeah, sure. Now in the contour, this contour section, there are multiple options, but in the normal way, we can mention the electric field and we can represent the electric field and magnetic field in the contour plot only. But for the surface current representation, we generally use the arrow. Okay. Now this is the arrow representation of the surface current. Okay. You can also first have to change this term. Just go to surface current, right take absolute, then take contour to arrow, and then here maximum 0 dB. The same things you have to. Okay. This is better. Now see the arrow direction. This arrow direction is shown you the surface current direction of this structure. And if you see the coloring, you can vary with the help of these units. Okay, and with the help of this scaling term. But the arrow is very small and the density is very high, you can say. Means it is hard to observe the arrow direction and the position of the arrow. Okay, the arrow value is the arrow size is very small. So for that thing, in 2D, 3D result, there is option this property. Go to this property, plot property. See, here you can change the scaling of your arrow in the arrow and bubble section. You can change the scaling, its minimum size, aspect ratio, density of the arrows. You can, I will reduce the density. See, this is more than enough to represent your surface current. Okay. And the minimum size is very small. So I can large this. This one. See, also you can decrease the density. Now, this is the proper representation of the surface current distribution. So, my concern is after seeing these type of results, how effectively you represent your result. That is important. So, this thing is important and you have to take care about it. Okay. This is the complete 2D analysis of any structure. Okay. So I'm in for the absorber, I'm covered the S parameter thing, then the formula for absorption, then formula for normalized impedance, and how we can observe that normalized surface impedance, whether it is in accordance with our structure or not. Then we have covered the um, physical mechanism of this structure with the help of the E field, H field, and the surface current, and how we can change its representation or the visualization of these type of results with the help of the units and the properties of the size and bubbles. Okay, these things we are covered. Now, uh, in previous hands-on session chat, I have saw a query regarding the parametric sweep, how we can um, mm, optimize the structure that someone asked. I don't. Okay. So briefly, I will cover those things also. So directly go to the, just close this result, just close this E and H surface current, close all this term. Now again we are coming back to our structure. Initially we observe all the results, but the three things are important to analyze the complete analysis of your structure. One is two things. One is the optimization, how you will find out whether your structure is completely optimized or not. This is the first part. And the second part is the analysis of the angular stability. And in the angular stability, there is two terms, phi variation and theta variation. Means polarization angle variation and the incident angle variation. Okay, that we will see in the next 20 minutes. For the optimization, as if you for when you are designing your structure, if you are choosing direct numeric value, then you are not able to uh, optimize your structure. Okay, that's why I'm always telling you, it's the better way is always make a variable for any parameter, for any thickness, for any radius, for any geometry, always make a variable. So in the parameter list, all the parametric value which you are applying in your structure is already shown. And if in some cases, if you not see this parameter list, and if you not see this navigation tree, or if you not see this message menu, then in the view section, there is a window term, this one, second last. Go to this arrow, and here all the terms are there which we need in our structure. What is the progress? What is the message? Where the navigation tree? Suppose this part is gone. How you can identify? Then go to this view section, then go to window, and on this navigation tree, it will come. Okay. Similarly, all the things you can manage with the help of these windows. Okay, coming back to our optimization technique. So we have that amount of parameters. Okay, a minute. Yeah, this thing. See, we will back to our optimization technique later. First, we will discuss the uh, mm, angular variation. Angular stability of your structure means the theta and phi variation. How you can check what about how the structure behave at different incident angle and at the different polarization angle. Okay, for these two term in the parametric list, there is two term. One is theta and one is phi. See, theta is the incident angle and the phi is polarization angle. Okay, theta is incident angle, phi is polarization angle, and initially its value is 0 because I am doing it in a TE mode. This phi 0 means TE, phi 90 means TM, and in between there are multiple polarizations. Okay, and this is theta. Theta means incident angle variation. Ideally, I am applying it as 0. 0 means ideally I am applying this term 0. 0 means I want a mm, I want a I don't heard that name. Okay, ठीक. Just a minute. Yeah, this thing I'm clearly shown this thing here. It is clear that terahertz plane wave in TE mode is incidented normally. Normally means theta 0 from the z-axis to minus z-axis. Okay, it is clearly mentioned here. That means all the basic results, means all the step-by-step results and all the f parameters and all these basic results are done with theta 0 and phi 0. Wave is incidenting normally on the top of that surface. This is theta and phi term. And in some case, it may be possible that these two terms, it may be possible that these two terms will not present in your parametric list. If it is not present in your parametric list, that means in the simulation, if it is not in there, then you can't analyze the angular stability result. Okay, then go to the simulation, then this boundaries, in boundaries, that is the phase shift. Okay, that means here directly 0 value is written. If here direct numeric value will there, then you are not able to see this term in your parameter list. So first write theta and phi here, and whatever you want you can write here, and then press OK key. Then you will able to see these terms, and these terms are also there, and all the other parameters will also present here. Then directly go to home. In the home there is a parameter sweep. Go to this parameter sweep. In parameter sweep there are different sequence, and in each sequence you can put your new parametric value. Okay, suppose right now I'm choosing the sequence 1. In sequence 1 I just want to change my theta. Okay, I just want to check the incident angle variation, how incident angle changes, and the what the absorption result will change. So in the parametric sweep parameter, the value you have to choose this theta term. I will already cover the basic of these things in the first lecture. So I will go to the faster way. The theta term, and if you want your step size is in a linear way, then you have to choose the linear. Otherwise, you have to choose the arbitrary point, and you can put your arbitrary points whatever you want directly 10, then 15, then 35, then 90. And if you have linear, means you want to check 0, 10, 20, 30, 40, then from 0 to 80. In case of theta variation, means in case of incident angle variation, we can't simulate it at 90 degree. Okay, we can't simulate it at 90 degree. And why we can't simulate it at 90 degree, and how the after analyzing the theta variation, what are the orientation of the antenna, I will show you. Just wait, just a minute. I will give you the little bit idea about how you can. Okay, this is my structure. This is my structure. This is the normalized line, normal, perpendicular. Again, now if I am doing these things at theta 0, at theta 0 means your signal this way, and that directly it will come like this. So ideally in the in practical scenario, you have to put your both the horn antennas in this way directly. And suppose if I am changing it, this is my Tx, this is my T, and this is my R. Okay. Now I want to change my incident angle. I have to check it in the different incident angle. So now this is the theta 10. Okay. So I have to place my transmitting antenna here 10 degree, and accordingly our receiver antenna will also shift like this, and the similar manner this is for 60. So my receiving antenna is also placed here. That means as theta increases, you have to place your antenna. In CST, it will directly put all these things. Means when you are selecting the theta 0 and theta 80 and theta 50, it will automatically shift its both the ports accordingly. But in practical, you have to take care of these things. Theta will goes like this. So your transmitting antenna will also goes like this, and the receiving antenna will also like this also. Okay. I can say this is my theta at 85 degree. Okay. If I am placing my antenna at 90 degree like this, and putting my receiving antenna at 90 degree also, this is meaningless because your structure is designed here. Here you have designed your structure or simulate, means fabricate your structure. And if you are putting your transmitting antenna at the at 90 degree, then the incident signal will not emit directly, not meet with this surface. Okay, that's why I am telling you the 90 degree of theta is not possible in the case of absorber. And the placing of your transmitting and receiving antenna is in this manner. Okay. That's why I'm putting the 0 to 80 degree, and you can place number of sample and the step width. I am putting it step width 10 degrees. Press OK. This is the theta 90 degree. And if you run this structure, then in the bracket 9 linears, that means 0 to 80, 9 results will come. Okay. If you run directly, 9 result will come in the same sequence. This thing is important. In the same sequence, if you write in the same sequence 1, if you put another variable, suppose same sequence, new parameter. Suppose I am want to vary my phi value, polarization angle. Okay, polarization angle we can vary from 0 to 90 degree. Okay, suppose I am writing it 0 to 90 and only two term, 0 to 90, and number of sample is 2 only. I just want to check my result in a TE mode, and I just want to check my result in a TM mode. So we have to choose 0 to 90 and number of sample 2, or you can check at the different step size, step width with respect to 5 or 15, whatever step size you want. Okay, just take over. So in sequence 1, in the phi there is 2 term, in the theta there is 9 term. If you run directly, that will gives you the all the possibilities of these two result. Okay, 9 to 18, total 18 results will come at this time, because at phi 0, it will run for all these theta value. Again at phi 19, it will run for all the 9 theta values. So 9 into 2, 18 results will come. But if you not want to that type of result, means all the combination, then no need to put the phi value here. Just delete this term. Okay, make a new sequence, then make a phi variation, give it to 0 to 90, number of sample 2, press OK. And now that will give you only 11 results, 9 for this and 2 for this. Just run this. You got 2 results for this value and you got 9 results for this value. And one thing is very important. Just go to this option, this one. Go to this option. If your theta is running, suppose if your theta is running, and where it will end at theta is equal to 80. If it end in at theta is equal to 80, that means in the parametric list, just a minute. Okay. If the theta is run till 80 degree, so it may be possible that theta value will change here from 0 to 80. Okay, it will 80 here, and if will 80 here, then upcoming results means at phi 0 and phi 90, result will come with theta 80. So for that you have to choose this option key and tick this one, this restore parametric value after a parametric sweep run. That means whatever value is here at the time of the parametric sweep, starting of the parametric sweep, that value will restore. Okay, this is very important. So this thing we can do the parametric analysis of the angular stability of this is the angular stability variation. Now similarly we can do the parametric analysis of this design also. If you don't want this thing, then delete all these, new sequence, go to here, A, suppose let R1. Okay. After clicking this R1, I am applying the R1 value is 4.9, but you can check why not 4.8, why not 4.7, and why 5, correct, exactly 5, and we can't go beyond 5 because this R1 is the radius of your patch and your unit cell length is at in the one side the unit cell length is 5 only, because one side it is 5, one side it is 5. The total length and width of the substrate is 10. That's why you can't run beyond this. You can run, but there is no meaning of this. So in that way you can simulate your structure. In that way you can analyze all these resonating structure, all these dimensions, and check what value is best suited for your structure. Okay, just I will show you the result of your parametric results. Just save this. Okay, now here you can clearly see in the result, in the mix 1 DC, all the parametric value I have already simulated. Okay, like see here, R2 is same, R2 is same, R3 is same for the first for the first 4 result, 1, 2, 3, and 6. These 4, 1, R2 is same, R3 is same, R4 is same, R5 is same, R6 is same. Only we have changing the T value, where T is the substrate thickness. We are analyzing what thickness value is best optimized value for our structure and for achieving the best absorption result. Okay, likewise all you can do all the simulation, you can fix all the other parameters and vary one parameter and analyze what results you achieve and how you achieve the best result, because this is a multi-band absorption result, is a multi-band absorption result. So the important thing is what is the absorption value, what is the peak absorption value for any resonant frequency. This is the first thing we should take care about it after doing the simulation, after doing this parametric analysis. What is the peak absorption value? Second, we can observe the more than 90% absorption bandwidth, means like if we see this result. So what is the bandwidth for this? You just tick one marker here, you just tick one marker here, and you can observe the bandwidth of your second peak, also for first peak. Okay. The second thing is more than 90% absorption bandwidth. And the third part is the FWHM value. These three things are the most important things in which we can conclude our result. What what best combination is there? See, I am doing the 24 simulations. Okay, so based on your structure and how many dimensions and the variables are there, you have to do your simulation and your parametric accordingly. Okay, this is the part of this is the complete parametric sweep, the complete parametric analysis of the structure in terms of dimensions also, and we also see the angular stability of the structure, how we can observe these things. Okay, now we will make a array of the structure. Okay, I will close this thing. Let's close this. All the basic absorber analysis is completed. I will also close this thing here only. If we directly make a array for this structure, then the initial result will remove. So the better we just make a copy of this array. Here I will show you the 3x3 array structure, and similarly you can make a 5x5 or 7x7, 9x9, whatever you want, and what's your system capability for the simulation of this thing. Okay, open this. Can you explain? Okay, can you explain how to assign the ports once again? Assign the ports means for the unit cell. Okay, I will show you. Just a minute. Go to this structure. See, this is the front view. Just minimize it. Now, this is the structure, and this is the port which I have already applied. This is Zmax in the upper side, and this is Zmin in the lower side. And first you will see there is a gap between your Zmax port and your designed geometry. Okay, there is a gap between them. I will show you why there is a gap. And in the Zmin also there is a gap. Okay, this is the first thing. There is a gap between the port and your geometry. And the next thing is you are making a unit cell. And if you are making a unit cell and you want to analyze its result in terms of absorption and polarization converter, then you have to make a periodic structure of this unit cell. You can simulate it. You can simulate it by using only the single unit cell structure. You can simulate only the unit cell structure, but in general, we are simulating it in a periodic manner. And for that, we have to assign the periodic boundary condition. This is the x-axis, this one. I just show you the structure. See this axis, this one. This is the x-axis along this. This is the y-axis, and the but top to bottom, this is the Z axis. So when we are when you are making a array of this structure, from where you have to put your multiple unit cells in the X and in the Y axis only, in the X side and in the Y side only, and in the Z axis you have to place your antenna, you have to place your what I can say, the terahertz source, means whatever excitation you have to apply, which you have to apply in the Z direction. Okay, this thing is clear. In the Z direction, X direction and Y direction, what we have to do. Then for this, for the assigning the ports, go to the simulation part. In the simulation, go to the boundaries here, the first way. And in the boundary, directly it will taken as a unit cell, but you can change it. If I will not change it here because the result will, I will show you this part here also. Just wait, just wait. In this structure, there is no result. So we can change any parameter accordingly. Okay. This is the structure. I just remove this. Okay, we can change directly. We can change. Simulate boundary. In the boundary, in the x-axis and in the y-axis, you have to put the unit cell, unit cell, unit cell, so that it will make a periodic boundary condition, periodic structure. And in the z-axis, you have to make a open add space, open add space, so that there is a gap between your structure and your geometry. Suppose if I am giving this as ET0, see, after putting this ET0 term, right now he is taken ET0 in all the four port, all these X min, X max, Y min, Y max. But in general, this X term, because in the X axis there is a electric field, then that means in X term it is ET0 and in the Y term it is HT0. Okay, this is the thing. And in the Z axis there is a open. So this is the condition when you want to uh, do a single unit cell structure. And if you want to make a periodic structure, you have to put it a unit cell. Okay, I think now it is clear. Okay, one more thing I will show you. See, when in the Z-min, Z-max direction, I am opening this as a add space, there is a space. And if I am just open it without making any add space term, then see this. In the Z-min direction, only open term is there. Then it is only open, but there is no space between the geometry resonating means your structure and the port. And in the Z-max direction, there is a open and add space. So there is a gap between these two terms. Okay. Have to change this. Done. So this is the unit cell structure, and now I will make it as a 3x3 array of this structure. Okay. For the array of this structure, one thing you must remember from the initial point of view. I'm just copying this structure. Okay. I'm just copying it and I will put it here. Okay. I will show you. This is my unit cell. This is my unit cell. And Right now, this unit cell is at the center. This unit cell is at the center, and the length and width of this unit cell structure is in the x-axis, and in the y-axis is 10. 10 micrometer I have chosen. That means this point is -5 and this point is +5. Okay. That's why it will make a 10. This is -5. This is 5. This is my axis. Okay. Now I just make a copy of this structure and place it here. Okay. Or I can place it here, so that this will make a 1 cross 3 structure. Right now it is 1 cross 3. 1 row in the 3 column. If we make a in a vertical way, I'm copying these three term and copy it here and here. Then it will make a 3 cross 3 structure. But just be remember how much, in what direction you are copying. Suppose I am copying this term in this direction. Okay, this is -5, this is 5. So what is this value? This is 15. 5 plus 10, 15, and this is 25. Why I am telling this? Because it is important when after making this array, when we are putting a waveguide port, because here we can't put a directly fluctuate port. If we make a fluctuate port, then again this 3 cross 3 will turn into a 9 cross 9 or 27 cross 27. Okay, so directly we will make 3 cross 3 and we will applying a fluctuate port, so that it can run that 3 cross 3 part only. That will not make any periodic structure anywhere. So at that time, this value is important. What is the initial value for -5? What is the initial value for this x max term? And if you are making the copy on that direction, this one, this one. That means in the y-axis also, what is, please repeat once again about the reason. What reason? Why I am applying the fluctuate? Why am I applying the waveguide port instead of fluctuate port? Okay. See, this is the unit cell. This one, unit cell. Only single cell is there. In the boundary, if I am making it in the boundary, if I am making this x and y as a unit cell for creating the periodic structure, then it will create a 3 cross 3 structure by its own. But it will, but see, it will make a periodic structure, but the fluctuate port is assigning in the one unit cell only. See this one. Okay. Or you can also simulate this. Means if I don't want to simulate it as a fluctuate port, then go to this waveguide port. Directly you can't go to that waveguide port. Boundary. Make this x min, x-axis electric ET0, in the y HT0, and in the z add open space, because in the y z axis we have to apply our waveguide port. Okay. Now go to this waveguide port. In the Z direction, just tick the Z direction. Okay. And Z in the port 1, I will, wherever you want to apply. Port 1, I just want to make in the upper side. So just choose this negative symbol. Okay. See this. Position is, what is the position of your port? This one. From where you are applying your waveguide port, that we have to select in the position section, where you have to mention the xmin, xmax, ymin, ymax value. And we know our xmin is -5, xmax is +5, ymin is -5, our ymax is +5. That's why it is already mentioned. Okay. So proper waveguide port is assigned having the same length and width with respect to your structure. Apply and then put a negative positive side and again apply. Now see. At that time it will only simulate the unit cell, complete unit cell. And the same phenomena we are trying to use in the array structure. In the array, we are just making 3x3 array structure. We are creating this 3x3 array structure. We have to know our this xmin value, this xmax value, this ymin value, and this ymax value. Okay. And we have to apply a waveguide port on the top and the bottom of this side. Yeah, good. Okay. This is the case. So for this unit cell, first I will remove this port. Just delete this. Again, just delete this. You have this structure. And how you make a copy? You just make a copy and just transpose in this section. That's why I'm not telling you about the transpose and the scaling and the mirror of that structure. Go to this component section. I will see directly we can see what I am doing. All the in the component, all the component have their copies. One thing is just copy the ground plane, just paste it here and then rotate it, or you have to make it by its own. That are the first thing. Second thing is all these sub elements are in the component 1 section. Okay, in this component 1 section. Directly go to the tick this component 1 section, means tick you are taking the complete structure. Your geometry means your resonating geometry, your substrate and your ground plane, all you can select from here. Then go to the modeling, then this transform section. This section is transform. Go to its arrow. There are 4 terms. One is translate. Okay, translate means these terms are you can see in your signal and system term. Translate, scaling, mirror, rotate, all the things are there. Translate means directly shifting. Okay, so you can translate, you can shift your structure. So I am just click this one. Right now, both the terms are highlighted. See, both the terms are highlighted because I am press this component one term, which cover both the terms. If you want only one, then you have to choose each component one term. Okay. Here, when you are opening this transform, yeah, or scale or rotate or mirror, whatever you want, you can choose it here. And then because I want my initial copy at the center only. That's why I just have to take this copy file. Copy means the initial version is still there, and whatever shifting you want to do, it will reflect in your screen. In the x-axis, in the y-axis, in the z-axis, in which axis you want to shift your structure, you can do it. Like if you by the calculation, if you know the exact value, you can put directly how much shifting you want in the x-axis, and you can put a variable value also. You can scale, you can shift its value in a variable way, and accordingly you can change it. Or if you don't with the help of the calculation, if you don't know the exact value, suppose now I just want to shift this structure, this complete structure in the left side of the x-axis, in the left side of the x-axis, then how much I have to travel, I don't know, I'm not able to calculate. Then directly press this arrow key and go, and the value 20 in the x-axis minus 20 is shown, and I know my parameter is going in the 5 or 10 ratio. It will not like this 19.5. 19.5 means there is some merging between two terms. Okay, I will click this and I will take the OK. 4x4 structure. But I don't want this thing which I have done just before. So for that, go to this history list, and in the history list, I am doing two type of translate here. First initial one and the second one. I don't want this second one. So we are deleting, delete. Okay. After this, okay, you have to update it. Update. Close. Okay. Again, we will come to our initial one. Now I just want only one copy. I just want only one copy. So you can choose the first one and paste it in the left side or in the right side. You can choose the second one and also paste it in the means shift it in the left side or right side, whatever you want. So my opinion is, because unit cell is in the at the center, unit cell at the center. So if you are making 1 cross 3 cross 3, or if you are making 5 cross 5, so why do your structure complex? Just make a one copy in this side, make a one copy in this side. So you know the structure is minus 20 to 20, minus 10, 15, 20 to 20. Yes. 15 to 15. I will show you. Now, clearly you have to select the initial term in which underscore one term is not present. So press the control key, take this one, and this one. Initially, all the component I have chosen. Then again, go to translate, make a copy, and I don't know how much I have to travel. 10. Okay. Done. These three things is completed. In the x-axis, in the y-axis, you want to make I can add the, see, after translating it or after scaling it, anything you can do. All the parts are shown separately. There is a, this is the part, that means we are not adding all these metallic ground plane, or in the substrate we are not adding all these things. If the material is same, you can add all these terms. Okay. Like inner circle, inner circle, inner circle, mid circle, outer circle. Initially, inner circle, mid circle, and outer circle. Make them together so that only one component, one subcomponent you have to translate. First, I will choose the ground plane. This ground, this ground, this ground. Take this, go to the Boolean and directly press the plus key and press enter. Directly you can press plus key and enter. Or by using this Boolean function, go to this add section, it will add. See, there is no line. This is the line for your working plane. See, now that will come, but that view, the back side, select view, go to this view, back side. This one will after front view. Okay. All the ground planes are only a single ground. First, I will add the substrate. All the three substrate. Directly press the plus key. It will add without going in the Boolean function. Okay. There is no gap between the two substrate part. And rest all, press the shift key, select all and press. See, in the component, there is only three terms. There is no confusion and we have 1x3 structure. Just save this. Okay. Again, I am opening this working plane so that it can easier to you to understand in the positive or negative from where I have shifting my geometry. So again, it will come. This is the main line. The center is at 0 and one structure is in the left side of this unit cell and one structure is at the right side of this unit cell. Okay. Again, select this component one, go to where modeling, transpose, translate, copy, and where I want to copy. Now in the y-axis, this term. This term till 10. Because I am going in the y direction, upward direction, that's why it is plus 10. When I am shifting it in the lower direction, I will put it as a minus 10. Make a copy, copy by tick, and then OK. Directly press the OK button. And again, two substrate will come. See, again, two substrate, two ground and two inner circle will come because we have making it. At this time, if you are adding these ground and these substrate, then it will be very difficult to you how you paste one extra ground or one extra substrate or one extra resonating structure. So better way is first rotate it or copy it or translate it, then add this. Again, take this ground, press the control key, this circle come in, it is written as a inner circle, but it has all the resonating structures and this substrate. Take both three, go to translate, translate it, make a copy, If you don't make a copy, at that part this is gone and here it is pasted. Now I will directly know I have to put -10. Okay, review. After putting any value, without directly clicking the OK button, you just have to tick this preview button and see whether you are correct or not. Yes, it is correct. Now OK. Now my structure 3x3 array structure is completed. Okay, just add these things. Ground, all the ground I will add. Inner circle _1 _2, add this. Substrate 1, substrate 2, add this. See, this is the 3x3 array structure. If you want to simulate 5x5 array structure, then you can make a 5x5 array. If you want to make a 10x10 array structure or 11x11 array structure, you can make it accordingly with the help of these terms. You can also make a mirror as well for making the other structure. I am using the shifting. Okay, now this is the structure and this structure we have completed. Okay, now we have to assign the boundary condition, and in that point we have to put a waveguide put, because now we don't want any other surfaces, any other cell, so that it will make a bigger surface. I just want to stuck in this 3x3 array structure only. Okay, so for that, go to, I will already explain you in the this file. So I will put this thing, simulate. Okay, you have to put the waveguide port, but before putting this waveguide port, you have to apply the boundary condition, and after applying the boundary condition, then you place your waveguide port, and then you are ready to simulate your structure. So frequency is okay, 3 to 14. Okay, go to this boundary. It is already, because we have done this earlier, that's why it is already applying. Okay, this thing is clear, because in this structure, this is the electric field direction, this is the magnetic field direction. That's why the electric field is ET0, because I don't want any other meta surface in any side. I just want to stick my structure within this range only, within this boundary condition only. This is the boundary condition. In the x-axis, ET0, ET0. In the y-axis, HT0. This is HT0. Just check all these things carefully. HT0. Okay. ET, ET, HT, HT. And in the Z direction, yeah. In the Z direction, open add space, open add space. And then press OK. Now our boundary condition is completed, and we have to place a waveguide port at the Z axis. Okay, so because see, after this boundary condition, still there is no port. Port option is empty. There is no port. That's why we have to make a port by its own. So go to the waveguide port, click this option. Initially, the CST wants to put your waveguide port at the x-axis, but we don't want. In the x-axis, we have already applied the ET0 term. Y also we don't want. In the z-axis we want. That's why take this z-axis. I just want to make my port 1 in the upper side. So I just change this thing. Okay. And see these values. See these values. If it is correct by default, if it is correct, then it is okay. But if it is not correct with the boundary condition, if it is not correct, then you have to put all these values manually. That's why you know these things. What is your min x direction? What is your min y direction? Max and max. Okay. Right now this is all okay. X min is minus 15. My min is minus 15. This is minus 50, 15. Minus 15 to 15. That means 30. 30 micrometer is the length and width of this 3 cross 3 array. And we know each unit cell is 10. Then 30 cross 30 is also there. Okay. This is okay. Now just till now we have only applied this waveguide port for this negative orientation. Press apply. It is already applied, that you can see in the port section of this navigation tree. Then in the Z axis only, you have to change your orientation from negative to positive. Means bottom to upper side, this direction. Okay. Again take okay. The second port is also applied. This is the complete array structure of this unit cell metamaterial terahertz absorber, and instead of applying the fluctuate port, we are applying the waveguide port here, and now you are ready to simulate your structure. See, again this thing is there. You want all port, or you want only one port, or you want only two port. Okay. So if you want all port, you choose both the term, but for that, the simulation may take some extra time for running the both side of simulation, but you already know the other side of simulation is not required for your structure because the ground plane is completely metallic patch. So better to simulate only port 1. It will taking so much time, and I am using my laptop, so I will not simulate it. I just abort this simulation. Okay, but simulation is running, and if time will goes on, simulation will complete and you got your result, whatever result will achieve at that time. Okay, I am not simulating this structure because I already have the simulated one. I just open that file and I will show you the result. Okay, the similar thing is there. The same thing. Port 1 is placed at the top surface of this absorber, means the meta surface, and the second port is at bottom. Similar thing is there. This is the top view. This is the side view of your structure. See, the same thing we have to do. We just, if we simulate this, the in the 1D result, the S parameter will come, and when S parameter will come, you just go to the post processing, just go to the template, put the formula, and you can simulate it. Okay. So just what is happening. See, this is the result. All the three peaks we are achieving after using this 3x3 port as well. Okay, and you can also analyze the, I'm not analyzing these. Okay, the port is shown here. So we just take the right click and hide this port. Port is still there, but I am just hide it. Okay, I will hide these ports, but port are there. And again, you can see now see. Because here E field is confined at this in this direction, and H or surface current is in this direction. Why? Because at the time of applying this boundary condition, in the X direction I have applied my ET0, and in the Y direction I have applied my HT0. That's why this will come. You can change this value for better representation also. Likewise, you can do your thing in the array structure. So this is the concept for array. You just make a simple structure. You copy all the components, substrate, dimensions, and all the resonating structure and ground plane. You just copy it wherever you want. You just know the starting and ending point of your array structure or your meta surface. Then accordingly put the waveguide port on that and simulate it to achieve the result. First, it will give you the S parameter, and then you will do all the things. Okay, this is the complete analysis for this paper, where you are able to do all these things, designing and the analysis of the complete results, whether it is 1D results or it is 2D results. Along with, we are also making an array of 3x3 structure, and we will see how we will applying the fluctuate port and how we will apply the waveguide port, so that we can simulate this structure. And multiple in the modeling, there is many terms, there are many things which you can do. Whatever you are using, it depends on you how you make your structure simpler. See, in this part, all the components are shown there. It is very difficult to analyze all these things, but here it is very easy. And whatever you are done, all things are saved in your history list. At any time, if you think any part you are doing mistakenly, then you can delete those things. Either it is port assigning, or it is frequency selection, or it is component designing. You can delete it here. Okay, there is no issue. And you can also hide the structure part of. Then suppose after press the right key, you can hide the structure. For taking the pictures and all these things, you can hide this. But if you hide these things, don't assume that there is no resonating structure. If you simulate this thing, it will give you the proper result. Okay, you just hide it, just so. And multiple substrate and metal materials are there. You can choose different materials also, means you can also all the structure is same, but you directly change the substrate value, means substrate design material and color. You just change the material whatever you want, and you get those results also. Okay, this is the complete uh, designing of the array and their simulation. Okay, this thing is completed. Now I will told you about the Desambo, means what I am telling you about the assignment. For the assignment, just give me a minute. Tomorrow we will see how to design a wideband terahertz absorber, because this is a multi-band absorber, triple band. This is a multi-band absorber which we have designed today lecture. So tomorrow we will discuss about the multi-band absorber and wideband absorbers, and we will also see how which type of materials are used for designing a wideband absorber instead of multi-band absorber. Okay, we will see in the next hands-on session, and we will also creating a graphene structuring material. Okay, just a minute. This. If you don't have IEEE access in your institute, then I will send you this paper in the group. In the WhatsApp group, I will send this paper to all of you, and you just have to, this is the, you not need to worry about this thing. You just want to make this ultra thin multi-band polarization independent terahertz absorber, where what you have to do in your assignment, I will tell you. You just design this structure, all the dimensions and all the setting is already mentioned in this paper. So you just have to design this structure. This is the step-by-step designing procedure. You have to follow these and make the final structure. Okay. And after that, you just find out this result. This ART result. You just have to find out this final ART results, means absorption, reflection, and transmission, and this R and T. will make you, this is basically a S parameters, and after applying the formula you get the absorption curve. And then if you can also try this angular stability thing and this one, because there is 1, 2, 3, 4, 5, 6, more than 90% 6 bands are achieved, then 6 resonating frequencies are there. That's why the simulation is at this is a surface current. The surface current at all these resonant frequency. Yeah, I will share this paper in this WhatsApp group, because I know many of you have not accessed this IEEE paper. Okay, this is the topic of the paper. I will send you. So make this structure by its own, simulate it, and send. We will just a minute. This paper will be shared on Canvas. Okay. We will share this paper on Canvas in the section material section. Okay. I will upload after this session. Then you can download it and do your simulation work and submit your assignments. Okay. Okay, that's all from my side. Hello. I think hello, Swati ma'am. That's all from my side.
Okay, sir.
I think.
Dear participants, next session is from 4 p.m. It will be a technical talk from 4 to 5:30 p.m. You are requested to kindly join on time. Thank you very much, sir.
Okay, thank you. Anandi Meena Bose. Hello.
Yes, sir. You are audible, sir.
Yes, I am audible. I am giving a mic to this Anandi Meena Bose. You can unmute yourself and whatever you want to say, you can. Okay. Maybe it is because of mistake. Okay. By mistake, it is hand raise is option. Okay, no issue. Okay, thank you very much. Thank you all.